In the previous videos, you assessed what data you have and how to use that information to establish a baseline. Now that you've established a baseline, we'll look at the savings mechanisms that cause your pumps and fans to use less energy when you implement energy conservation measures. This will help ensure that you only apply calculations, tools, or rules of thumb that are based on valid assumptions about how your system operates. Before considering the specific savings mechanisms available for pumps and fans, it's important to ensure that any calculations reflect how the equipment actually operates, to avoid under or overestimating your savings. Let's start by looking at the three savings mechanisms for pumps or fans: reducing flow, reducing pressure, and improving equipment efficiency. While different savings opportunities may utilize specific savings mechanisms, it's important to always consider the system as a whole. For example, in an uncontrolled system, reducing the pressure may cause the equipment to automatically increase the flow, thereby reducing the overall savings. The first savings mechanism to consider is to reduce the flow. Opportunities for reducing flow through your pumps and fans include eliminating bypass or excess flow by right-sizing the equipment, or switching to a variable frequency drive and turning pumps and fans down or off when not needed. You can also reduce flow by fixing leaks in the system. Reducing flow by turning off pumps or fans when they're not needed has a direct relationship to energy savings because it reduces the time component of the energy equals power multiplied by runtime equation. When it comes to reducing pump and fan flows, the amount of energy savings depends on the characteristics of your system. If flow reduction is achieved by throttling the pump flow via a valve or a damper in the case of a fan, the pump or fan speed remains constant, and the system curve changes so that the operating point moves along the pump curve. This can reduce power relative to higher flow rates, but the savings are typically minimal. On the other hand, if the flow is reduced by reducing the pump or fan speed, then energy savings follow the affinity laws, which state that power is proportional to the cube of the pump or fan speed. In this case, reducing the flow rate will move your operating point down the system curve. It's important to note that in systems with a high static head, where the fluid is lifted a significant amount, the change in the system curve means that the affinity law will overestimate the savings. Affinity laws also lose accuracy when considering larger changes in flow, for example greater than 10%, because they do not account for other factors such as changes in motor efficiency or other system interactions. The second savings mechanism is reducing pressure. This includes both the static pressure and dynamic pressure of your system. There are opportunities to reduce pressure on both the supply and demand sides of the system. To change the supply side system pressure, you can use VFDs to eliminate dampers and throttling valves. To reduce the demand side system pressure, you can increase pipe or duct diameter, clean or replace filters, or remove blockages or other obstructions. Look for ways to reduce friction in the system. You may also be able to reduce static pressure by reducing how high fluids need to be pumped. Reducing the pressure will change your system curve. Because pump power is directly proportional to pressure, less power is required to deliver the same flow at a lower pressure. To realize these savings, your system must be able to adjust the pump or fan curve down to match the system curve at the desired pressure. Left unchecked, a reduced pressure can cause the pump or fan to increase flow beyond what's required, wasting energy. By using a VFD, the pump or fan speed can be reduced to better match requirements and achieve energy savings. For example, in an uncontrolled system, reducing the pressure may cause the equipment to automatically increase the flow, thereby reducing the overall savings. If a VFD is not available, another option is to right-size the pump or fan. You'll also need to consider how the changed system curve will move your pump away from or towards its best efficiency point, as this can impact the expected savings. The third savings mechanism, increased efficiency, involves either ensuring that your pumps and fans are operating at their best efficiency point, BEP, or upgrading them to higher efficiency equipment. When improving efficiency, it's important to remember that pumps and fans will have different efficiencies at different points along their pump curve. It's not just about purchasing a more efficient pump or fan. It's about making sure that your pump or fan is operating close to its best efficiency point most of the time. Understanding these three savings mechanisms and how they interact will help you make accurate assumptions in your calculations and avoid estimated savings that don't reflect reality. For example, if you're reducing flow or pressure, you should also consider the impact on the efficiency of your pump or fan to see if you should right-size the equipment or improve efficiency by using a VFD. The last step is to identify appropriate savings calculations. In the next video, we'll apply what we've covered so far to select a savings calculation approach that's appropriate for your system and energy conservation measure.